Welcome my dear friends to sharmaclassesnagpur.com. Here we are dealing with the Maclaurin's theorem, which will again include the Leibniz theorem now. So before starting with we are using cross multiplication, which is y into 1 minus x square is equal to sine inverse x. So this is the question itself, and now differentiating with respect to, let this be equation 1. Differentiating 1 with respect to x, we get first function into differentiation of second function plus second function into differentiation of first function, we get this thing. And so now afterwards, in order to simplify, if I take LCM over here, so this root under root 1 minus x square becomes 1 minus x square y1 minus xy is equal to 1, because this root under root 1 minus x square in the denominator gets cancelled. Let this be equation 2. Again differentiating with respect to x, first function into differentiation of second function plus second function into differentiation of first function minus common xy1 plus y, this is 0. Simplifying, we'll get 1 minus x square y2 minus 2xy1 minus xy1 is minus 3 times xy1 minus y is equal to 0. This is equation number 3. Now applying Leibniz, to equation 3, x as it is, n plus 2 plus n minus 2x y n plus 1 plus n minus 1 by 2 factorial minus 2 yn. To the second term, again Leibniz, minus 3 common, x as it is yn plus 1 plus n 1 yn. Now to the third, yn is equal to 0. Simplifying this thing, first as it is, first function as it is, taking xy n plus 1 common from second and fourth, minus also common, 2n plus 3 xy n plus 1, again I am taking minus common, this 2 gets cancelled, and yn also common, so this is n square minus n plus 3n. So this becomes 2n plus 1 again yn, this is becoming 0. Again simplified form of this thing is 1 minus x square yn plus 2 minus 2n plus 3 xyn plus 1 minus n plus 1 whole square yn is 0. This is equation number 4 for us. Now as the algorithm we can use put x equal to 0 in equation 1, 2, 3 and 4 to get y when x was 0 is equal to 0, y1 at x equal to 0 is 1, y2 at x equal to 0 is again same as y of 0, that is 0, and y n plus 2 when x was 0 is equal to n plus 1 whole square, y n of nothing means it is always parenthesis 0. So this becomes now our main equation, and which is also proved. This one is now proved. Okay, so let this be equation number 5. The second algorithm now, when we put n equal to, when we are putting n equal to 1, 2 and 3 in equation number 5, so we are getting y3 of 0 is n equal to 1, 1 plus 1 2, 2 square 4, 4 times y1 of 0. So y1 of 0 is 1, so it is 4 into 1, that is 4. And when n was equal to 2, it is becoming y4 of 0, and 2 plus 1 3, 3 square 9, 9 times y2 of 0, but y2 of 0 was 0, so 9 into 0 is 0. Then n equal to 3, y5 is 0, becoming 3 square, 3 plus 1 4, 4 square is 16, 16 into, we are adding y3 of 0, but y3 of 0 is 4, 16 4s are 64 now, 16 4s are 64 and so on like this. So we are putting all these values in the Maclaurin series to get the final result, that is y of x, and y is nothing but the function itself. So sine inverse x by under root 1 minus x square is y of 0 is 0 plus x into y1 of 0 is 1, so into 1 is same thing, plus x square by 2 factorial, y2 of 0 is 0, so again 0, plus x cube by 3 factorial is 6, and into y3 of 0, okay, we are having as 4, so, and x raised to 4, y4 of 0, so y4 of 0 is again 0, so no need to write or 0 plus, and so like this, x5 by 5 factorial into y5 of 0 is 64. So the final answer we get as is equal to 0 plus x plus this 2 2s are 4, 2 3s are 6. So this becomes 2 by 3 of x cube plus 5 factorial is 120. So this is 64, this is 120. 8 8s are 64, 8 15s are 5 factorial. So this becomes 8 by 15 of x raised to 5 and so on like this. Thank you my dear friends in watching. Thank you.